So this is a second paper on mobile crowd sensing. It's called First Learn, Then Earn. So there is something like a reward, which is the earn part. What do we earn? We earn in terms of cost of mobile crowd sensing campaigns. But we need to make some effort to learn. What do we learn? We learn the user preferences, how different users assess crowd sensing tasks, and how do they respond to incentives. So this is what the paper is basically about. It's a joint work with colleagues from Athens University of Business and Economics and Business, Iordanis Koutsopoulos and Michalis Titsias. So this is a highly introductory slide, maybe slightly redundant. All it tries to say is that there is a huge pool of users out there which could be recruited for crowd sensing applications. So basically, I'm referring to all those users which move around the city, having smartphones in their hands or in their pockets, with all its rich sensing capabilities. So smartphone sales, there are some signs that they have reached some saturation level, but there are already some billions of users out there which essentially could contribute to these applications. So this is one way to think about crowd sensing applications. There is one block that has to do with the collection of data from the crowd. And here we are concerned with things like how to select users and sensors, how to provide incentives to them to make contributions, and of course privacy aspects. How could users make their contributions without really sacrificing what they perceive as private? This is running mainly on the client side of the application, and there is a second block on the backend server usually, where you pick up all these small contributions and you make something bigger. What's this bigger? It might be some informational application, maps, environmental, pollution maps, whatever, or something more interactive which could serve as an assistant for the user, so helping him select more cost-efficient routes in the city or find a parking space faster. And almost always, there is another block which collects data about the user, which does not necessarily relate to this type of information. It's rather information about how the user moves, what are his choices, his preferences, how does he or she respond to different triggers, payments. And this is what comes roughly under the term user profiling. And this user profiling then can be used in order to make more efficient, to inform the provision of incentives. So these two kinds of tasks, user profiling and monetary incentives, is where this presentation is focusing. For the first part, the learning part, we more or less draw on machine learning techniques, and I will have to invest some effort and slides to set up some common terminology to be able to understand each other. And then there is a second part which has to do with the allocation of incentives. This is the optimization part. My understanding is that the community is much more familiar with this. But before doing this, let's try to set the problem a bit more precisely, so nothing fascinating here. There are some tasks which are geographically dispersed across a city or part of the city. Each of these tasks is described by some attributes, so the task might give some reward to users for contributions. It has a location, so someone should go there to make a contribution, take a photo, report on its status or something. And it might also have some scope, so it might be, a more commercial service, someone makes money out of it, or it might be more a community service, so it might be like these maps I mentioned before. And then we have the users. These are the users who run the application, who have subscribed to the crowd sensing application, and they have their own preferences. So some of them might be more into this for making some money in their spare time. Some others might be more for the social thing, this community contribution. And we make two fundamental assumptions, I guess, that differentiate our approach from the main body of the literature. The first one is that the last word is with the users. So the application may present to the users different alternatives, makes offers to them, but eventually the users are the ones who make a choice, and they might even choose not to contribute to a task. So this is different than assumptions made usually that some tasks are essentially assigned centrally to the users, and probably better reflects the uncertainty that exists in these applications as to whether users will contribute. And this is also closely related to a second assumption, the fact that users are non-rational entities which do not necessarily try to optimize some utility function which is analytical and can be described, fully in closed form. So this more or less goes back to the bounded rationality thread, which is a very long thread in behavioral sciences like cognitive psychology and behavioral economics, and argues that users, humans, actually satisfies. So they might end up with a good enough choice, even if this is not the best one. Now, quite a central choice in our approach was to see the task choice as a classification problem. The classification problem is one of the most popular machine learning problems. What do we usually want to do with this? We have some sample, and we want to assign it to one of two or more classes. And how do we do this? By looking how this sample scores on a feature set. Already 3 terms that need somehow to be explained, probably with an example. What could be a sample? Someone, let's say a person who has some symptoms, a headache, and goes to the doctor's office to be examined. This is a sample. Then the doctor needs to make a decision. Should he be further sent for admission to a hospital to get more treatment, or should he send back home with some medication? These are 2 classes, right? The positive recommendation for admission is class 1, and the other class is send him back home. And how does the doctor make the decision? By considering some features. How much is the blood pressure of the user? How much is the temperature, the heartbeat rate? Ideally, he will consider these 3 numbers in some way, and will take a decision to classify him in one or the other class. Now, there is not just a single model to do classification, and there is no solid theory to tell us which is the right model according to the case we have at hand. So it's more an art thing, and it involves a lot of trial and error. But in any case, what we need to do with any model we choose is some training process. So we need to find the parameters of the model, and these parameters also define this boundary. So this boundary separates classes, and whenever we are given some feature values, it should tell us directly which class should the sample be assigned to. So this boundary here is linear. It does not have to be linear, and it does not even have to be perfect. So this means that some of these blue samples, let's say patients that were judged by the doctor not to be sent to the hospital, essentially in the end ended up in a hospital for further treatment. So the boundary may introduce some misclassification, and this misclassification is actually one criterion for assessing how good a model is. The choice we have made for the classification is to take one of the most well-studied and understood classification models, the logistic regression one. This is a probabilistic classification model. So what does it return? It returns a probability that a particular sample should be assigned to the one or the other class. And this is this probability. So it's a sigmoid function due to its shape. It's like a sigma. For low values of x, you're close to 0. For high values of x, you're close to 1. And in the mean range, you have this transition area, which might be steeper or broader depending on the actual values. Here there is also a feature weight vector. So this is a vector with weight values that actually show what is the importance of each of these feature values. So to each of these 3 measurements, temperature, blood pressure, we have to somehow say which measurement is more important for the decision. So there are some weights that do this thing and let you and affect the overall probability of classification in the end. So this is for 2 classes. There is some generalization to k classes. This is called multiclass logistic regression, but In this paper, at least, we more or less stick to these kind of cases. So now let's come back to the problem after this diversion. How does this all relate to the crowd sensing? For us, classes correspond to crowd sensing tasks. There is the feature set X relates to the task attributes. In a simpler scenario, the one that we more address in the paper, this feature set could include the distance of the user to the task and the reward, the payment the task makes to him for a contribution. And here a fundamental remark is that, okay, some of these features have to do with the task, are fixed, and we cannot intervene with them, but that some others, and basically the payment, the incentive part, is controllable. It's something that we can play with in order to achieve some stuff. We'll see what we want to achieve later. And there is the feature weight vector WU, which in our case is user-specific. So this weight, feature weight vector exactly reflects how each user assesses different aspects of the task. How much importance does it attribute to the payment? How much importance does it put on the distance, etc. And someone could simplify it, say that for us in this problem, I mean, users correspond to feature weight vectors. And how do we get these feature weight vectors? They result from a training process, which becomes separately, it's carried out separately for each user. How does this go? We need a training dataset, which has a number of samples. Each sample is a combination of a vector and a scalar value. The scalar value takes binary values. So we see in the past, out of the choices, when we offered some tasks to the user, how did he respond? Did he take the task? Did he make a contribution or not? 0 or 1? And what were the particular feature values for that task? So what was its distance? What was the payment it was given, etc. And then how we proceed is more or less fixed. We have to build the likelihood function to estimate this vector. And then we call for maximization of this algorithm, of the logarithm of this likelihood function, which is equivalent to the minimization of the negative. There is a penalty term, which penalizes large weight values. We don't want large weight values. For machine learning guys, this is straightforward to avoid some overfitting. And we come up with an unconstrained optimization problem, which can be solved for the single global minimum through some example, some iterative gradient descent algorithm, as long as we are a bit careful with the step of the algorithm. So this process gives us a very solid path to find these feature weight vectors, to characterize users, and what do we do with them? Somehow we need to get into the optimization problem. In our case, what we try to do is to optimize the expected quality of the contributions that are accumulated, attracted over all tasks. Right? So this Q here is a value which takes values between 0 and 1 and measures how skilled is a particular user for a specific task. So how good a contribution can he make for a particular task. There is some budget. We assume that each task comes with a budget. And we also set an upper bound on how much we can pay a single user for a single task. Now, this problem is quite complicated, so it's a joint problem. We have to choose simultaneously for which tasks are we going to make offers to a particular user, and how much payment should we offer to him or her. But there are some cases that are somehow simpler and lend to more easy treatment. So one simpler case is when we have a single task. We have an application that is only made in order to collect contributions for a single task. So in this case, we save the question of how to determine which offers to make, and we are left with a pure payment allocation problem. In this case, we compare our algorithm with 3 alternatives, which we call preference agnostic. So they know the user, they know how good he is for one task or the other, but they are quite lazy, and they don't really put the effort to find out the preferences, so how much he is interested in the distance aspect of the task or the payment, etc. So one simple alternative is to take the budget of a task and split it amongst the k users that lie closest to the task. Another one is to split the budget among the k users which are the most skilled for the tasks. And the third one is to do what you did in the second case, but make the payments proportional now to the skills of the user. This is a characteristic plot of what we get with these three alternative schemes. So you see that the value of k apparently affects the expected quality that is attracted, but the point to note is that in all cases you are somewhere below 12, for this particular example with budget 40 and 50 users, while with our approach you can get something which is 25 to 30% higher. But that's a simple case. Let's go to some other case. One case is, another relatively simple one is when the application only wants to take a single user for its task, so wants to do one-to-one mapping. This is the case with mobile crowdsourcing applications like Twitter or Koiki. Koiki is a kind of crowdsourced packet delivery service. So all these kind of applications that really need one person, no more. In this case, okay, it's quite simple to form the bipartite graph with tasks on the left, users on the right, and put as weights on the edges the probability with which each user would go and contribute to the particular task if the whole budget of the task was given to the particular user. So people who are familiar with algorithms would know that this is an instance of the maximum weight matching problem. And for this kind of problems, we are quite safe. So there are algorithms that solve it optimally and exactly. So I'm coming back now to the general problem, which is a more stringent kind of problem, more difficult to face. So in order to get a kind of indication of what we gain by all this effort, the additional effort to learn individual preferences, we make some decoupling of the two tasks involved in the problem. So we separate how we determine which offers to make to each user from the payments from the allocation part. And there are some simple rules to do this. For example, one rule would be make an offer to a user for the task that is he lies closest to. Or make an offer to a user for the task that he or she is most skilled for. And then what we did is to run some simulations, so throw in a rectangular area a number of tasks and a number of users, and apply both schemes, our scheme and the alternative ones, the user preference agnostic. And we try to get a feeling of the gain. So this is the objective function value with our scheme, which is approximately optimal. This optimal should not really confuse. And this is what the objective function value with the alternative. And we see that this, depending on how the offers are made, this gain ranges from anywhere from 20 to 30% and 36 to 55%. Now, this is what happens when the application makes a single task offer to a user. Now, there are some good reasons why an application should not make just one task offer to a user, but more. And here we have some evidence from cognitive psychology, but also from marketing. Marketing people know it very well, that people want to have some comparison reference when they make a choice. They don't feel really comfortably when they are presented with just one option in a take or leave it question. And probably the most strong, let's say, demonstration of this is the decoy effect, what people call decoy effect. And a case study which is very popular in this sense is the Williams-Sonoma case study. So what is the Williams-Sonoma? A company that sells cookware to households and to even professional chefs in the United States. At some point in the 90s, they wanted to launch for the first time a bread maker. They made an exhaustive market research, and they decided to launch it at the price of $275. The response of the consumer was not really very good. And then, instead of withdrawing or doing something else, what did they do? They launched a second product with marginally better service offer, so some extras only, but at a price which was considerably higher, something like 50% higher. And what do you think was the response of the consumers? Well, this one didn't sell, but the sales of the original took off. So this more or less acted as a decoy for this particular brand. So they saved this brand by just offering the user an asymmetrically dominated second option. So somehow we try to accommodate this in our formulation. So we let for paired offers to be made to users. And if you see again the formulation, it's pretty straightforward to do some manipulation here and get again some weighted sum of sigmoids. Again, we have a problem which is fundamentally difficult. It's a joint problem. And again, we can follow a similar path to simplify the situation. So we can have some simple rules for determining how to make offers. Here we make offers to a user for the two tasks that lie closest to him or for the two tasks that she or he is most skilled for. And then again, the same thing. Go make some simulations, consider different instances, and try to see what our scheme gives against what the alternative schemes give. Here there is again a gain which ranges from 5 to 16, 18%, and a smaller one in case the offers are made according to the tasks that the user is most skilled for. Now, this is not supposed to say that this is better than this, because if someone checks the absolute values, it will see that whenever the tasks offers are made for tasks that the user is most skilled for, the absolute value of the optimization of the objective function is much higher. Yeah? So trying to recap what we did, we more or less revisited some basic questions in a problem which has been investigated quite enough in the past, yeah? The incentive provision problem, trying to be more pragmatic in a sense about how users behave and how users respond to the tasks they are offered and how do they respond to the incentives these tasks provide. And to this end, we turn to the toolbox of machine learning, and let's say a strategic choice was to see the task selection problem as a classification problem. Now this resulted in some new formulations for the optimization problem, for the incentive provision problem, which sent us more or less in the direction of sigmoid optimization and the possibility to exploit some recent results about how to solve such problems. It comes out, at least the results suggest, that all this extra effort to invest it on learning individual user preferences pays off. So you have some gain against approaches that do not get into this mess, which sometimes exceed 100%. We saw that they are smaller when you have two offers. Is there more to do in this direction? We say yes. For us, it's a kind of thread that has started. What are things that someone could look into? One thing has to do with the objective function. So we more or less, we consider the aggregate expected quality of contributions. This is a social welfare type of objective function. Someone could have something like a fairness type of function where he would or she would ask that each task is guaranteed some minimum quality. A second thing has to do with the generalization into applications that go beyond the two tasks and present a user with, let's say, 4 or 5 task offers, giving him more flexibility to choose from. To this end, there is, I guess, a quite implicit path. It's we quite know how to move, at least with respect to the learning phase. It's less clear how far can we go with this multiclass logistic regression model in terms of optimization. And I would say the more far-reaching objective is what happens in online settings. So in our problem, we implicitly imply that the allocations and the decisions are made all together, somehow synchronously. You know what is the set of tasks. It remains constant over some time. You know the number of users. It's also constant over some time. And then you do this allocation. Now, there is a question, what happens when, in the more realistic case, when tasks come, are submitted over time, and when users come and go. And I think this finishes my talk.